Hello friends, welcome back to the lecture series on applied statistics and econometrics. So, let us have a look at today's agenda item first. So, we will start today's lecture with a brief discussion on a new probability distribution, and that is called students T distribution, and then we will continue our discussion on interval estimation. We will discuss the case of mean for unknown sigma, and then case of mean for small sample, and then we will also discuss the case of population proportion and case of variance. And finally, we are going to end today's lecture by have a discussion on sample size determination. So, today's lecture will start with students T distribution. Now, why we have to learn about one more distribution? It is because so far we have dealt with the case of large sample where the number of observations n is greater than 30, it is assumed, but if you have a small sample where n is less than 30, then the standard normal distribution that we have made use for confidence interval building will not work, and I will show you why. And so, we need to figure out some solution, and statisticians have provided us the solution. So, we are going to here work with the students T distribution. Okay. So, now let us going to have a look at students T distribution, its key features. So, what is the task at hand? So, our task is to estimate the mean of a normally distributed population in situations where n is small and sigma is unknown, and that is a quite common case. So, to solve this problem, Gossett proposed a statistic called students T value, and that is defined as T, and that is equal to the difference between sample statistic x bar and population feature or population parameter mu. The difference is divided by the root n. So, this initially may look a bit complicated, but you know this T value that I am showing you, the formula here inside the red box, do not you find the similarity with some previous discussion that we had? If you remember in the last class when we were discussing the case of confidence interval, then actually we had sigma in place of small s in the formula, right. So, it is very similar to what we have been doing in the recent past. So, now this T distribution, it is a new probability distribution with n minus 1 degrees of freedom, and this is the sampling distribution of the T value. Now, why degrees of freedom? Because of course, you see the formula of T involves S, the sample variance, and we all know that to calculate the sample variance you have to first calculate the sample mean. So, there are actually n minus 1 independent observations. We have had a discussion on degrees of freedom before. So, hopefully you remember that, and that is why T distribution has n minus 1 degrees of freedom. Now, let us have a quick look at the most interesting properties of students T distribution. So, note that the T distribution, like a standard normal distribution, is also bell shaped and symmetric around mean, and we will derive, actually we will not derive in the course, but you can derive it easily that the mean and median for the T distribution is actually 0. So, now we come to the second property, and that is saying that for a T distribution with V degrees of freedom, the mean and median is 0 if V is greater than 1, and variance is V divided by V minus 2. Now, the third property says that after 30 degrees of freedom, it implies when we are dealing with large sample, the T distribution is very close to the standard normal distribution, and if it is less than 30 degrees of freedom, it implies when we have small sample, then the tails of the T distribution are thicker than those in the standard normal distribution. So, now let us look at students T table, and this students T table will help us to figure out the probabilities corresponding to different values of alpha and V. So, as in the case of normal, we had taken the help of a standard normal table to compute various probabilities. In the case of T also, we are doing the same thing, because the PDF and CDF of T is also very formidable look wise. So, it involves integrals and it will take a lot of time if you want to derive everything on a piece of paper on hand or using a calculator. So, to help you, statisticians have made this table available, and let us see how we can make use of this table. So, again like the standard normal table, students T table is also in a kind of matrix format. So, here we have rows and we have columns. So, row shows the values of the degrees of freedom, you see it starts from 1. Well, we will not get this kind of case in practice, because degrees of freedom 1 means that we are talking about n equal to 2, only 2 observations, but anyway they have given us the values. So, you see these goes till 30 for all values of V, and then after 30 there is a break, and then they are reporting the cases of 40, 60 and 120. Actually, why? Because after the V crosses the value 30, then actually you do not need a student's T table. You can actually make use of the standard normal table as an approximation, and it will be a very good approximation. So, that is why after 30 people do not report the different specific values of V, because it is going to be very lengthy otherwise. So, now the column. So, the columns actually give us the value of alpha, and what is alpha? It is the tail probability that the random variable small t will take values greater than t star with V degrees of freedom. So, each and every cell here that you see for a corresponding row and the choice of alpha, here these are not probabilities. You can very well see that these are not fractional numbers like bounded between 0 and 1. So, these are not the probabilities. These are basically the values of the t variable on the t axis, right. So, these are basically the cut points, you can say, on the t scale. Now, we are going to look at the picture of the student's T curve and the standard normal curve, and we are also going to draw some conclusions based on these curves. So, first let us look at the diagram that is in the upper part of the slide. So, here I am showing you the famous standard normal curve using this red colored bell shaped curve, and as we all know that for standard normal the mean is 0. So, this is centered at 0, and now against the standard normal curve I am going to show you two T curves, and they are for different degrees of freedom, because of course, as I have shown you in the previous table that the cutoff values on the T scale, actually these degrees of freedom determines the spread of the distribution when we are comparing T distribution to the normal distribution case. So, here we are showing you two different cases. One is for a very small sample where the sample size is 4 and degrees of freedom is 3, and the corresponding curve is given in lilac or purple color or light blue color, whatever you want to call it. And then I am showing you another T curve for degrees of freedom 15, and that is in thick blue or dark blue color. So, as you can see here that the T curves are much flatter towards the tail compared to the standard normal curve, and the gap between the standard normal curve and the T curve actually decreases as we increase degrees of freedom. So, what does it mean? So, it means that as the degrees of freedom increases, it implies the sample size increases, then the probability that the T random variable will take a value higher than value T star, that can be approximated by the standard normal curve as the degrees of freedom increases, because the difference in the probability for the approximated number from the standard normal table and the actual probability coming from the T table is going to be small and smaller as the degrees of freedom increases, and finally when we hit degrees of freedom 30, then actually in practical sense there is no difference. So, the bottom part of the slide now is going to show you an example how to find a critical t value and plot them in the t curve. So, here we are showing the case for n equal to 5, and if n is equal to 5, then we can assume or fix the level of confidence at 95% or 1 minus alpha that we have discussed before. Now, for these two values, let us see how we can figure out the probability from the student t table. So, remember that we have 1 minus alpha equal to 0.95. So, that area actually is given by the yellow colored area, and that is bounded by two different critical values minus Tc and plus Tc, and we have to figure out these threshold values minus Tc and plus Tc from the student's t table. Now, how to actually find these values? So, note that from this 1 minus alpha equal to 0.95, that is an assumption, of course. From there we can figure out that alpha actually takes value of 0.05, because alpha is basically split into two parts here in this diagram. So, if they are equal, then each area will be alpha by 2, and that is going to be 0.025. So, now we know that we have to look at the table for the v value of 4 and alpha value of 0.025. So, now let me go back to the previous slide, and then first we go to the row and we spot 4 here, and then we move rightwards across the columns, and then we will look for the column title 0.025, and then we stop, and we see the t value reported there is 2.776. So, the example that we are showing you here in this diagram, for that example the cutoff values or the critical values or the threshold values, whatever you want to call, it is going to be plus minus 2.776, and I have indicated these two values in the diagram. Now, we are going to discuss the case of building confidence interval for population mean from sample mean, when the sample mean has come from a small sample, and it involves the use of students t distribution and the students t table. So, let us have a look at different steps. So, the first step is to calculate the sample statistics, and we know that what sample statistics we need to calculate. So, of course, the mean given by x bar, and then the sample variance, and then from the sample variance we have to calculate the sample standard deviation. So, sample standard deviation is given by small s, and that is basically the square root of sample variance, and we have taken care of the degrees of freedom concerned. So, that is why we are dividing by n minus 1 here, and this is a good proxy when the sigma is not known. So, now from step 1 we move to step 2, there we have to identify degrees of freedom. So, if we have n number of observations in the sample or n data points, then we have to subtract 1 to get the degrees of freedom. Then we need to fix the level of confidence and then find the corresponding critical value consulting the students t table, that I have shown you how to do. So, if you assume that 95% level of confidence, then you have to go back to the students t table, and then you have to figure out what would be the critical value corresponding to a particular degrees of freedom that you have calculated. Okay. So, now the fourth step talks about the determination or calculation of margin of error capital E, and that is basically given by the formula in the corresponding red box. So, that is basically the critical value that you observe from the t table shall be multiplied with s, the sample standard deviation, and that then should be divided by root of n. And once the E is determined, it is time to find the left and right endpoints and then form the confidence interval. So, once the E is calculated, we know what to do. We have to subtract E from the sample mean x bar, and then that will be the lower limit of the confidence interval, and then we have to add e to x bar as well to find the upper limit for the confidence interval, and if I want to write an expanded final expression, then it looks like kind of clumsy, but actually it is very simple because I have already explained you what to do, and you see that for mu, the unknown population mean, I can write the final expression of the confidence interval in the small sample case. Okay. So, now let me move to the case of population proportion, because population proportion is also a population feature that we may be interested to know about, but we have to make use of some small sample to infer about it. So, in that case how to proceed. So, again we are going to look at a step by step cookbook approach. So, we are talking about 6 steps here, and the first step actually is to identify the sample statistics n and x, and then from these two data one has to figure out the point estimate, and that is given by p hat equal to x divided by n, and x is of course the number of events or some outcome, and n is basically the total number of data points or observations that we have, out of which x number of outcomes have been realized. And then in step 3 we have to find out whether the sampling distribution can be approximated by the normal distribution or not. So, when we realize the x and n's, then they can be modeled actually in a binomial setup, but as we have studied earlier, and I told you that binomial can be approximated by the normal distribution in the large sample case. So, and there are some statistical criterion to be met, of course. So, first we have to figure out whether we can actually approximate our sampling distribution for p hat by a normal distribution or not, and for that what we have to do, we have to check whether n times p hat is greater than equal to 5 or not, and n times q hat, which is basically 1 minus p hat, is greater than equal to 5 or not. And then we have to find out the critical value ZC if we indeed get evidence for normal distribution assumption in this case. Then we have to fix the level of confidence, and then we have to consult the Z table to get the critical value ZC. And then finally we can actually get the margin of error, and that is the formula given in the red box, and that is capital E equal to the critical value ZC times square root of p hat q hat divided by n. And once we get this E, next step is to find out the left and right endpoints of the confidence interval, and that is basically done by subtracting E from p hat, and that is basically will give me the left endpoint or the lower limit of the confidence interval, and then if I add E to p hat, then that will give me the right endpoint or the upper limit of the confidence interval, and finally the confidence interval has to be written in one compact expression, and that is basically the last box that is showing you. Okay, so now we are going to look at the sample size determination problem again, because when we did it last time, probably it was done in a hasty manner, or as you have not done confidence interval prior to it, probably you did not understand what is W, what do I mean by error margin and all, but now we have had sufficient discussion on these concepts, and probably if I talk about it again, then probably it will be easier for you to appreciate and remember. So, I will not spend a lot of time, maybe a minute or two to discuss the sample size calculation formulas again. First, I will start with the case of the population mean, and of course, we want to get a proxy value of population mean by making use of the sample mean, and if that is the case, then how we can get the sufficient number of n or sample size. So, there is a rule. So, given a critical value associated with a predetermined confidence level, So, note that you have to first fix the confidence level, and then of course, there will be a critical value ZC associated with that fixed alpha, and then maximum error of estimate capital E, we can actually figure out the minimum sample size requirement n to estimate mu from the population mean, and that formula n is given here. It is not new to you, you have seen it before. So, it is the critical value ZC times sigma divided by E and the whole square. So, if sigma is unknown, then okay, no problem. If you are dealing with a large sample, then you can use a proxy for it by calculating S, the sample standard deviation, that works in practice when you have a large sample. Next we move on to another rule, and this is for the population proportion. So, again we have to assume that the critical value we know, and that is for a predetermined confidence levels and a margin of error E. So, you have to fix E and the alpha values, and then the minimum sample size required to estimate P can be done using this formula n equal to P hat times Q hat and then ZC, the critical value, divided by E square. Now, this formula assumes that you have an estimate for P hat and Q hat, but what if you do not have the estimates for P hat and Q hat. So, I told you earlier also, so if you do not have a priori information, you can also make use of 0.5 as the proxy value for P hat and Q hat. So, now we are going to look at one example where I am going to show you how to find confidence interval for unknown population proportion. Now, where is this exactly useful? So, you see, just right before the election in any country, many independent research organizations conduct surveys or public opinion polls, and they try to give some kind of an idea about the likeliness of a political party or a candidate to win certain election. So, not only in India, in US also and in many countries also these public opinion polls are conducted. Now, of course, sometimes their forecast matches, sometimes their forecast does not match the reality, but well, how do they address this problem? So, for that they actually make use of this statistical estimation theory, and I am going to show you one particular hypothetical example. So, let us assume that there is a political party, and that party is going to contest one assembly seat, and they want to know about their chances of winning that particular seat. So, they have hired an independent research organization. So, that research organization will conduct an opinion poll to investigate the party's chances in that particular seat. So, to start, that organization has collected 200 randomly chosen voters, and they have surveyed these 200 people, and out of this 105 indicated that they are going to vote for that party, and other 95 indicate that they are going to vote for their opponent party. So, in this case, as a statistician, how do you find a 95% confidence interval for the proportion of the population who actually intend to vote for that particular political party? So, I have already shown you the steps in the previous slides. So, if you follow the steps, the first step would be to find the sample proportion P hat, and that is given by x divided by n. So, how many said yes? That is basically captured by the variable x, and a particular value of that variable x is small x, and that should be divided by the number of sample size or number of voters in this case. So, you can get the sample proportion value of 0.525, or you can say 52.5% of the respondents have said that they are going to vote for the party. Now, the next step would be to find the critical value of z. Now, why z? Because look, we have 200, that is a large sample, and then if you multiply that number 200 with the p hat, and also the q hat which is 1 minus p hat, then you are going to see that it satisfies the criteria that we have set for normal approximation to discrete data in the case of population proportion. So, in that case we can actually safely apply the standard normal table to find the critical value for 95% confidence interval. Now, 95%, why 95%? Because that is the standard norm, you can make it 90% confidence interval as well. But for that you do not have to go back to the standard normal table again, because remember I have spoken about one magic figure, and that is the z critical value for 95% confidence interval, and that is 1.96. So, this magic figure we are going to use here, and not only here later also in the case of hypothesis testing you will see that we will make use of this number again and again whenever need arises. So, the next step would be to find the error margin capital E, and I have again shown you the formula how to compute error margin, and if you plug values in that formula you will get 0.069. Now, the last step is to find the limits of the confidence interval for population parameter p, and we all know what to do. So, to find the lower limit you have to subtract that error margin from the sample proportion. So, if you do that then you get the value 0.456, and to obtain the upper limit of the confidence interval you have to add that same error margin to the sample proportion, and if you do so you get a value of 0.594. So, this is the way you can actually construct the confidence interval for an unknown population parameter p in this particular example. Now, before we move on to the confidence interval creation for unknown population variance, let us look at a digression. It is not a very big digression in real sense, because you will see that when we will be discussing the case of confidence interval building for population variance, we are going to make use of chi-square distribution. We have already introduced chi-square distribution, but that is not in this lecture. So, just to make this lecture self sufficient, it is not a bad idea to have 1 minute or 2 minutes discussion on chi-square distribution first, and then look at the problem of confidence interval in the context of unknown population variance. So, just to remind you few basic things about chi-square distribution from the previous lecture, that chi-square distribution is based on sampling from a normal population. So, that is a mandatory thing. So, you can say that it is a strict assumption that chi-square distribution, if you want to deal, then the sampling should be from a normal population. So, the original data should at least look like a normal distribution, it should come from an approximately normal population. Then the second point is that the sampling distribution of a newly created random variable n minus 1 times the sample variance a square divided by population variance sigma square as a chi-square distribution. So, here note that n is my sample size and a square is basically my sample variance. So, that is the unbiased estimator of the population variance, and sigma square is unknown population variance, right. Okay. So, the last point that I want to mention here is about the mean and the variance of the chi-square variable. So, if you remember the previous lecture, chi-square random variables and the probability distributions, they always have associated degrees of freedom, and so if we assume that we have degrees of freedom k here, so the mean of the chi-square random variable will be k and variance will be 2k. Now, let us look at a diagram of chi-square distribution, and I am going to show you various things through this one single diagram. So, of course, in the x axis I am going to plot various values of the continuous random variable chi-square, which is defined as n minus 1 a squared whole divided by sigma square, and of course, along the y axis I am going to plot the probability value. So, basically it actually measures PDF. Okay. Now, I am going to show you two different chi-square probability density function curves. One is in orange, and that you see it is continuously falling. So, that is basically for the degrees of freedom 2, and then you see another PDF drawn, and this is in the pink color, and that is basically constructed for degrees of freedom 5. Now, you see that as we have increased degrees of freedom, there is a change in the shape of the PDF, and this will continue to surprise you as you keep moving the degrees of freedom values. If you increase the degrees of freedom values, say from 5 to 10, 10 to 15, and then 15 to 30, then you will see gradually the chi-square distribution is going to be flatter and flatter. So, the maximum distance of the curve from the x axis, that is going to decrease and decrease, and it is going to be more flat towards the tails. And note one thing, that for smaller degrees of freedom, chi-square distribution, actually it is a positively skewed distribution, and that is on the shape part. Now, we are going to look at interesting critical values and the corresponding probabilities associated with the chi-square distribution. So, here we are going to look at the left tail and the right tail critical value. Note that so chi-square is a very special distribution, it is not like the normal or not like the standard normal or even t, which are all symmetric. So, actually if you know one critical value, there is a mirror image of the other critical value, and you can write plus minus zc or plus minus tc. Remember, we actually use the trick for z and t, but this trick is unfortunately not going to work with chi-square distribution, because chi-square is an asymmetric distribution. So, you have to separately figure out the left tail critical value and the right tail critical value. So, let us assume that our confidence limit is 95%, and that is basically 1 minus alpha. If you remember the previous set of lectures, we have already introduced 1 minus alpha, and 95% is basically the most popular choice for 1 minus alpha. That is why I am talking about that. But I am going to show you in this diagram a very general case. So, it pertains to any other choice for 1 minus alpha. If it is 99%, then also you can explain through this diagram. If it is 90%, then also you can explain through this particular diagram only. So, in general sense, we can write that the probability of the chi-square random variable taking a value between the left tail critical value and the right tail critical value is 1 minus alpha. Now, how to find this left tail critical value and the right tail critical value? So, say we have 1 minus alpha equal to 95%. So, in that case alpha will take value 0.05. So, if you now subtract alpha divided by 2, which is going to be 0.025 from 1, then actually you have a probability value of 0.975. So, for the corresponding degrees of freedom, you have to find out the percentage point or the critical value chi-square, the particular degrees of freedom with respect to the probability value of 0.975. So, that will give you the left tail critical value, and for the right tail critical value it is simple. So, it is going to correspond to the probability value of 0.025 after dividing alpha by 2, and if you look at the corresponding degrees of freedom value, then you can figure out the percentage point from the corresponding PDF. But note that this is very complicated, because with the change in degrees of freedom, there is a change in the shape of the PDF of chi-square random variable. So, how can we find out the percentage points or the threshold values or the critical values, whatever you want to call them, and I am not showing you the form of PDF of chi-square distribution, because that is very messy and complicated. So, it is very difficult indeed to get these critical values yourself by calculating on a piece of paper. So, the statisticians have again come up with a statistical table, and they have actually provided us these different percentage points or the critical values for combinations of degrees of freedom and alpha value. So, with this brief discussion on the chi-square random variable and chi-square distribution, let us now proceed with the discussion on confidence interval of the population variance. So, as I told you that we are going to make use of chi-square distribution here. So, it is indeed very important to check whether the population has a normal distribution, or at least approximately it looks like it is tending towards normal curve and all, the relative frequency curve is tending to the tending towards the normal curve or not. And once that is verified, you actually have to identify the degrees of freedom. That is simple. So, you have to subtract 1 from the sample size, and that is your DF, and then you have to find out the point estimate sample variance, and we all know how to do it, it is not new to us. And then if the random variable x has a normal distribution, then the derived random variable chi-square follows a chi-square distribution. We have spoken about this in the previous slide only. So, it is also not new to you. This is basically not a step, actually this is just something in between that you need to remember. And that actually tells you that you have to consult the chi-square table, and you have to find the critical values chi-square right and chi-square left that correspond to a given level of confidence and the degrees of freedom. And once these left and right critical values are obtained, you can actually find the confidence interval by following this particular formula that I am showing you in the very last box in this slide. And you see that this has two endpoints. Now, the lower endpoint actually is basically ratio, and it is ratio of n minus 1 times the sample variance and the chi-square right critical value, and the upper limit of the confidence interval is the again a ratio, and this time n minus 1 times sample variance is divided by the chi-square left critical value. Okay. So, once this confidence interval is built for the population variance, it is very easy to find out the confidence interval for the population standard deviation as well, because you just have to take the positive square root of each end point, and then you will find the confidence interval for sigma, the population standard deviation. Okay. So, now I am going to give you this picture of chi-square table, which is coming from a textbook. Now, here again you see, like other tables I have shown you, this is also in matrix form, and the row actually a particular row shows the values of the degrees of freedom, and then a particular column gives me the value of alpha, which is basically the tail probability that the chi-square random variable will take values greater than a particular threshold value chi-square, say chi-square star, with k degrees of freedom. So, now with this table, let me look at an example, and through that example I will also show you how to consult this particular table and get the critical values or the threshold values from chi-square distribution. So, here is our example. So, suppose you have a sample of 30 students who were subjected to a particular test or exam, and the sample actually results in standard deviation of 12.23 points. So, in that case the task is to find out a 90% confidence interval for the sigma, the population standard deviation. Okay. So, now we are going to first look at the critical values from the table, because sample standard deviation is already calculated for us. So, there is no need to find out the sample variance. Of course, 30 is a large number. So, again we can assume that well approximately it is a normal population. It may not be, but let us assume because it is a simple example. So, now we have to find the critical value. So, we have to find the left critical value and the right critical value from the chi-square distribution, and that for that we need to consult the table. So, basically for the left critical value, the value is from the chi-square table, where degrees of freedom is 29 and alpha is 0.95. Why it is 0.95? Because you remember we were discussing about 1 minus alpha divided by 2. Here we are looking for the 90% confidence interval, that is why. So, residual is 10%. So, now you divide this 10% into 2 equal parts. So, it will become 5% towards the tail, right. So, you have to look at the table for the alpha value of 0.95 at the left tail, and then for the right tail you have to consider alpha value 0.05. Okay. So, now let us go back to the table. So, now you come down the rows and then you stop where you figure out df takes value 29, and then you move towards your right across the columns. So, my first task is to find out the chi-square value for alpha of 0.95, and from this table you can see that the value is 17.708. Now, my next task is to figure out the value for alpha 0.05, and you see it is basically the very next value in that same row, and that is 42.557. So, from this table we have got the values, and now the formula I have already shown you. After plugging these values of left and right critical values in the formula for confidence interval for sigma square, you get the lower limit value as 101.924 and the upper limit value as 244.947. So, if you take square root of these two numbers, finally you land up with the confidence interval for the population standard deviation, and of course that is a lower number 10.0. So, now we are done with our discussion on estimation theory. From the next lecture we are going to look at the other part of statistical inference, which is called hypothesis testing. Thank you.